I've been with NTOP for about 4 years. Prior to that, for a little bit of background, I was in the aerospace and defense industry for about a decade, and I primarily focused on CFD, thermal, and structural analysis for aircraft engine components. In and around 2017, I kind of, in a roundabout way, discovered the DPMS and its potential application for heat exchangers, did some investigation into those, and initially NTOP kind of brought me on to help bridge a gap between our tool and external CAE tools. Over the past couple of years, I transitioned to the solution engineering side of things, and since then have been helping a lot of our customers solve their most technically challenging problems, at least in the AM industry. A lot of my focus is still on the interoperability side of things, specifically around heat exchanger design and ways to automate now design exploration. A little bit of an agenda. We'll look at some case studies that we've gone through over the past 6 years or so. Talk about a handful of lessons learned or some core design principles that I've taken from them, and then we'll get into the automation side of things. So starting with our case studies, I'll take you on a journey through complexity, and first we're going to crawl. So in 2017, to my knowledge, the only way that we could create a gyroid TPMS was with faceted bodies, and I'm pretty sure we did this in Space Claim. This greatly limited the complexity that we had and that we could create with, and we had little to no control over our design parameters. This made generating meshes and inflation layers either difficult or sometimes impossible because the fluid domains captured the faceted geometry of the solid there that we see on the left. We tried to push this through traditional CFD tools, ANSYS CFX, ANSYS Fluent at the time, and we just couldn't find a mechanism to do that. I learned then that same year of ANSYS Discovery Live, and mind blown with the speed that we could start to solve and visualize these types of complex problems with. And so we said to ourselves, man, there's something to this TPMS, right? But is there a better way to model them? How can we actually use their full potential? A couple years later, we're going to start to walk now. So we introduced a proof of concept. We said, okay, let's take a fuel-cooled oil cooler. We're going to be inspired by others around us. And really, this was enabled by implicit modeling. You've probably seen this heat exchanger floating around the past couple of years. But what we're able to do then is take original sketches that we used to conceive this idea, the geometry that we used to create it, and because now we have access to advanced design tools, we have now control over discrete design parameters. We can capture the complexity that we want to use. And at the same time, because we're not generating these bodies with faceted geometry, we can start to evaluate the performance. So we can push them into traditional CFD tools. This first study was in ANSYS CFX, and it was, a lengthy chain of different tools to get there, but it was achievable. And we were able to answer the question is, are these structures feasible for heat exchangers and design? Absolutely, they are. Kind of near and dear to me is the countless lessons learned and hardships overcome in this overall design process for our proof of concept initially. Let's start to run now, right? We're going to pick up some speed. Our next kind of forte or challenge was compact heat exchanger design. So in this example, we reduced the volume of a traditional shell and tube heat exchanger by about 85% while maintaining a near equivalent working or wetted surface area. And we partnered with a couple other companies to move through this study in ANSYS and stress engineering, where we can now run full-blown conjugate heat transfer analysis. So the vertical section planes that you see there on the right show the interior temperature distribution along the fluid and solid regions. We can start to test these structures now. So we can see the unit there on its test bed. We did pressure to burst and flow heat transfer testing. Now, a few years ago, it's getting better now, but we were pretty limited to how thin we could manufacture the walls of the heat exchanger. And so you'll notice our working pressure in this case is 150 psi. We held steady at 2,500 with about a 500 psi on the low pressure side, and we failed at about 5,000 psi. So heavily over designed, but we were limited at the time to how thin we could ultimately print and manufacture these. We've come a long way now. We're at much thinner. We have much thinner requirements now. Our next kind of jump is we're going to start to fly. This is a work in progress for us. It's an air-cooled oil cooler. A lot of our previous designs, at least publicly, have all been liquid-to-liquid heat exchangers, and that primary reason has been the minimum feature requirement for additive manufacturing. We just can't get as thin, in some cases, as traditionally manufactured heat exchangers. As that changes, we can start to implement different fluid types through these types of structures. Some of the design characteristics that are going to go into this main design is the core of the heat exchanger is going to be shaped by CFD at the onset of the design. So before we even conceptualized what the overall structure is going to look like, we'll design what the core is going to look like first. We're going to be influenced by sensitivity analyses, DOE studies that we're going to look at. Basically, we're going to package 6 years of best practices, optimization development, and CAE integration. And as Erica kind of mentioned, we're going to print this without meshing, so direct implicit to EOS print. What this does is significantly reduces the file size. So we can go from gigabytes to megabytes. And in doing so, this enables increased complexity and part size. If a customer had come at me 2 years ago with a 75,000 unit cell TPMS that they wanted to try and print, I probably would have laughed at them. We can't mesh this. Your printer's not going to be able to handle it. With this type of file transfer, we really now have more or less infinite scalability in that regard. No loss of geometric fidelity. We're not discretizing, so we're not going to lose geometric features. And on the question of surface finish, we've actually seen improved surface finish, again, because we're not faceting the geometry. A couple lessons learned. These are very important. Flow distribution and control. The biggest one that we've learned over the few years is how we shape the plenum or the transition region into and out of the heat exchanger core. This does a few things. One, it's going to gradually introduce the flow into the plenum, and it's going to distribute the flow more evenly into the TPMS structure itself. This cross section is a little bit misleading just because of the nature of how these structures twist and turn as they grow, but we're actually feeding both the left and right sides here with this cold flow. To take a kind of step back, if we look at this bottom left image, pretend we're hot fluid and we're entering this top port here. The red is a physical barrier. It's a baffle that we put there to keep the two fluids from mixing. So now if I'm fluid and I'm entering here and I don't have a plenum region, all I have is these two little white dots essentially to flow into. So we're immediately going to be hit with a large reduction in cross-sectional flow area, which impacts pressure drop. And then the fluid itself is going to be less distributed within the core. So it's going to be less efficient overall. Other ways we can control the flow inside these structures are with physical baffles. So the image on the left kind of represents this. If we look at the blue baffle here, the hot fluid's going to come up. It's going to be forced to wrap around the top and exit out the backside. We can kind of see that physical baffle take place here. Another way we can control the flow is with something that I call virtual baffles. So let's presume we have a larger heat exchanger design, and where we have these gray discs, rather than introducing a physical baffle and let's say cutting off half of the flow area, what we can do is we'll choke the flow or change the cell size essentially in that small region. So if you follow my mouse on the right, we're moving through this red flow area. We're going to transition slowly to a choked region. We're not completely cutting it off. We're going to transition back to our normal flow area. What this does is it encourages most of the flow to move in and around the structure. So we're increasing the time that we're in the heat exchanger, but we're not impacting the pressure drop as significantly. Another important aspect, and this was one of the first characterization studies I did, was with regards to aspect ratio. And what I mean by that is manipulating the cell size in the different axes. So if we look at the top right, we have the X, the Z, and the Y axes. For an aspect ratio of 1:1, the cell size in all three axes are going to be equivalent. So I said, okay, what happens to my pressure drop now if I stretch the cell size in the primary direction of flow, or in this case, in the y-axis? How does that impact my pressure drop? And what we saw was as soon as we hit an aspect ratio of 1:2, for the gyroid in blue and the diamond in red, we saw a reduction in pressure drop between 40 and 80%. So pretty remarkable. Now, the caveat to that is we're going to lose out in surface area, right? So we now have two conflicting design parameters. I want lower pressure drop, but I want higher surface area for better heat transfer. So now you have to try and find a happy medium between the two. And it's, as an engineer, it's kind of fun when you have those conflicting requirements. Let's get into more of the fun stuff, the design parameters that we have available to us and how we can start to automate those processes. A question I get all the time is, what unit cell type should I choose for what type of physics? We're focused on heat exchangers today, so we're really, or two domain heat exchangers, I should say. So we're really just focused on TPMS unit cells. We can make some generic assumptions and look at the physical characteristics of these across the board. So let's assume that we have a 10 millimeter cubic unit cell, and either because of burst pressure requirements or maybe minimum feature size on our printer, we have 0.5 millimeter thickness, and we're going to print out of an aluminum powder. We can start to evaluate these parameters. Now, the first one we care about with heat exchanger, surface area. The lindenoid here at the bottom gives us the most amount of surface area, a little less than twice that of the gyroid, for example. But that's not the only important factor. In aerospace and defense, the mass is hugely important. So let's look at the mass of each of them and rank them. The lindenoid, why it gives us the most surface area, it's the second heaviest. The gyroid is the lightest. Now, what we can do is say, okay, let's look at some others. Bringing your attention to the diamond, it gives us the third most surface area, and it's the second lightest. It's looking pretty good. Beyond that, we might care about volume fraction. If we're concerned with permeability or porosity or ways to predict what the overall pressure drop through our structures might be like. And just as a side note, you'll also notice that the gyroid and diamond have very similar volume fractions. Beyond that, we care about mechanical strength. And so we can start to do homogenized analysis to look at a stiffness map, and we can then start to evaluate their mechanical properties so that they can survive the vibration of a launch or different types of mechanical loads. The design parameters that we have available to us are numerous. These are just a handful. I'm not going to read them all off. And these are what I'll call standard design parameters. With GD, with additive manufacturing, and just with where the CAE world is today, we have a new design parameter. It's the shape of our design space. So this is what I was talking about. Let's shape what our heat exchanger core might look like before we even select the lattice type. Presume we have our design space, both hot and cold fluid domains. We know what our boundary conditions are. We can run our analysis. We'll pull that data in, and now we can use that data to shape what our core might be like. We can be 100% influenced by the flow through the cold domain, or 100% influenced by the flow through the hot domain, or somewhere in between. So now we have the slider bar to help us control the flow better to impact the pressure drop. And in this little study, when I did this one, it kind of surprised me. The sweet spot, at least in this case, given the fluids and the boundary conditions, wasn't at 50-50. If I want the best of both worlds, in this case, I'm sitting somewhere between about 35% and 30% in this case. The blue line all the way to the left, we're completely influenced by the cold flow. The red line all the way to the right, we're completely influenced by the flow through the hot domain. So numerous design parameters. The ones we'll focus on for the DOE and the optimization study are going to be the mid-surface offset, lattice type, aspect ratio, to pull out some of the major ones. So what are the steps then to this automation process? First one, pretty easy, right? Determining the design parameters, and in this case, we're going to characterize to pressure drop. Lattice type, given. We want to evaluate all these lattice types and find out which ones we can eliminate, which ones are the most influential. The number of unit cells, both linearly as we stack them and grow the length of our heat exchanger, but laterally as well. How does that impact the overall flow? Aspect ratio, again, we're stretching the cell size in the primary direction of flow. These are the first three that we're going to look at, and then one that we're going to tack on in a few slides is the mid-surface offset. If you don't know what that term is, that's okay, I'll explain it. What we can do is we can take the surface that defines the gyroid here, let's say this green one on the left, and we can either pull it to the left or push it to the right. And when we do that, we're either going to compress or expand the flow area in either of these two fluid channels. And here's a little GIF to kind of help show you that. So in this case, we're pulling the green channel in, so we're going to be able to constrict the flow moving through that section. Oftentimes, we have different fluids moving through our heat exchangers, different viscosities, different pressure drop requirements. So now we have another tool available to us to help optimize and articulate the way that the fluid moves through our structures. The next step to automation is making our sample DOE table, and more importantly, at least in this case, is translating those design parameters to be encoded in NTOP. So for example, NTOP's not going to know what aspect ratio means. It's not going to know number of linear unit cells. In this case, design space height is the number of linear unit cells. The cell size in the z-axis is aspect ratio. The purple is 1:1, and the yellow is 1:2. Once we pull this table in and we encode that language into the block system or the way that the geometry is represented, we can start to validate that, our design iteration number is going to spit out the appropriate file that we want, or the appropriate geometry. After we have this working, the next step is refining the automation in NTOP. And really what this comes down to then is how we then export this file to this case, ANSYS Discovery or ANSYS Fluent, whatever you're going to run into. So a meshing step. We're going to export a surface MSH file, so native format to ANSYS CFD. And we're also going to export in this case, the inlet and outlet boundary conditions, or the name selections where we want to apply our boundaries. So how do we get from step A on the left to step B on the right, where we're batch processing hundreds of MSH files? Erica mentioned a concept of reusable workflows, and how we build those out, or a way to think of them, is custom blocks or user-defined block. In order to understand kind of what that means, you need to know that the notebook, or the working space of the software, is broken into three main segments. The inputs at the top, the main body here in orange, this is where we do all of the work essentially, and then the outputs here at the bottom in red. We can save this NTOP file, open it up in a completely different instance, and now what we've done is we've packaged all of this work here that we've blocked here in orange into one tiny block. Once we satisfy the input criterion, which in this case is simply just the DOE number, out spits the MSH file, and it's just going to run through, in this case, this list of 396 discrete design points. Now that we have the automation process refined in NTOP, let's move to ANSYS Discovery. I'm kind of sick of looking at this MSH file, so let's cover it up. But we'll pull in each of those MSH files. We can assign the boundary conditions because we have those named selections. And once we do that, the next step is determining what parameters we want to automate. So the input variables, definitely the material types. In this case, we're just going to do water. The constant flow rate, and in this case, it's per unit area. So for example, if I have a 1x1 unit cell, I'm going to potentially flow 1 kilogram per second through it. If I have a 4x4, it's going to be 4 kilograms per second. Pressure at the outlet, and we're going to set the fidelity slider to highest. Output variables that I was concerned with, at least at the time, was velocity streamlines as a PNG, and then pressure differential and maximum velocity as CSV files. I got most of this working. I could pull in a singular file, but I don't have a coding background. And so I have to give a huge shout out to my colleague Wasif, who helped me batch process all of this data. Without his support, I don't think I would have been able to realize this dream of mine. So once we have those two automated refinement steps completed, let's generate our final DOE table. Our first one looked at lattice type, number of unit cells, and aspect ratio. We'll generate that table, push it through the user-defined block, export our MSH files, batch process that in ANSYS, so that we can get to my least favorite part, at least, which was post-processing the results. I won't bore you with all of the details of the post-processing, but I do want to highlight some of the unique aspects and characteristics that I took from it. So let's compare now the TPMS unit cells. This plot, we have a 1x1 cell matrix and a 1x1 aspect ratio. The vertical axis is normalized pressure, and then the horizontal is number of linear unit cells. Right away, we can see that the lindenoid and Nuvius unit cell types have an immensely higher pressure drop compared to the other four, and they're also the two heaviest. So let's throw those out the window. We'll filter out this plot to just the gyroid, the Schwartz, the diamond, and the split P. Similar process of elimination with the split P, pretty high pressure drop compared to the other three. The Schwartz, in this case, has a highly irregular pressure drop distribution, or peaks and valleys. And really all of the unit cells kind of have that trend, but it's very prolific on the shorts. And so we can try and investigate why that's happening. So if we look at these two design points, this first one looks at a single unit cell, and the second one is 1.5 unit cells. So in this case, as soon as we're flowing into the 1.5 unit cell, we're immediately choked. We're immediately choking our flow. So this tells me if I choose to design with the Schwartz, I have to be very careful of where I chop that unit cell off as to not impact my pressure drop too much. But also, it gave us the least amount of surface area, so we'll throw that one out the window too. Gyroid and diamond. Right now, those in this little study are kind of the clear-cut winners. So looking at the gyroid, we're going to compare the cell matrices and the aspect ratios. So these first two plots are an aspect ratio of 1:1. The only difference is the cell matrix. So 1:1 versus a 2:2 cell matrix. This tells me a couple things. One, that if we want to start to parameterize and develop these sensitivity plots and characterize the unit cell types, doing it on a single unit cell doesn't make much sense. There's too big of a pressure differential between these two. The other thing it tells me, right, is, or the other thing it tells me is that fluid, it's always smart. It's going to take the easiest flow or the easiest path to get from point A to point B. So for the most part, a lot of the flow that we're pushing through these structures is more or less going to stay in its same little column. It's not going to deviate all the way to the right, move all the way to the left, and then exit out the bottom. And indeed, we do see that when we evaluate these structures in CFD. And then to stay true with our characterization from a couple of years ago, we saw a 44% difference in the aspect ratio. Pulling in the diamond now, a very similar trend, 68% difference. But now let's remember back to the physical characteristics of these 6 TPMS structures. The diamond ranked number 3 in surface area and was the second lightest. 21% more surface area than the gyroid. The diamond is pulling ahead. So now let's look at both the gyroid and the diamond TPMS, but with that mid-surface offset, or where we're going to shrink or grow the passageways through the discrete domains. In this case, we're just going to, the range is going to be from -1 to 1 in increments of 0.2. And this is kind of what that looks like. So -1, we're going to constrict the flow, so we should see higher pressure drop. 0 is the nominal or default, and 1, we're going to open the passageway, so we should see reduced pressure drop. We can start to capture the flow area, hydraulic diameter, so now we can start to assign and characterize real values to what we're seeing. Comparing the mid-surface offsets, we'll start with the gyroid. In this case, the blue line here at the top is the gyroid G, mid-surface offset of 0, and we're going to move down stream from there. So we're going to increase the passageway. And as you would expect, we're going to see a reduction in pressure drop. So now we have another tool, right, available to us for pressure drop. Aspect ratio, mid-surface offset. Diamond, we saw the same thing here in the dashed lines, similar trends. But now let's compare the two. Gyroid is the solid line, and diamond are all the dotted lines, and the color represents the mid-surface offset. So 0, 0.4, and 1. And all 3 of these conditions, we saw a significant decrease in pressure drop when we evaluate the diamond. While I've been piling through this data over the past couple months, and while I was building out this slide deck, I kept laughing at myself. I feel like 6 years ago, I was one of the first to start the gyroid train for heat exchangers, for infill geometries, whatever. And now I feel like I have to restart the train at least for the diamond. I'm by no means the first person to, realize the difference in the gyroid and the diamond, but still, it does not seem to be widely spread yet. And part of that reason, I think, is aesthetics, right? So the gyroid, it just looks sleeker to people. The diamond is a little more clunky looking. It's not as sleek, right? And we've actually given, let's say, 6 designs to the Department of Defense, for example. One design is a beautifully topology optimized part. It's organic looking. Then you have shell and infill with gyroids, different lattice structures, what have you. And they all meet performance requirements. And you ask the head honcho, which design do you want? They'll go for the aesthetically pleasing one, even though some of the others outperform the one that looks good. So aesthetics matters, not just in the consumer good industry, but in the aerospace and defense industry as well. In summary, there's still a lot of characterization left to do. We don't have a K's and Londons of these types of structures. It's going to be a collective effort of a lot of engineers, a lot of test facilities, printers to really develop and hone in on what TPMS is best for what application for this environment. We need to develop sensitivity plots to determine the most influential parameters to pressure drop, heat transfer, etc. And like we have seen, adoption of these structures is growing, but it's still not prevalent. But all of this is enabled by growth and improvement in the additive manufacturing world. So improvement in our design tools, our simulation capabilities, but really it's enabled by people like you, right, who continue to push the frontier of what's possible, to challenge our imagination, to challenge innovation and push boundaries. So I'll leave you on this slide of what inspires you, what applications can you think of? Thank you.